functions. Okay, so yesterday 15.1 we have already completed that part about equations of tangents and normals using our derivative. Okay, so increasing and decreasing functions will be what we're looking at today. Right? So we need to first understand what is an increasing function and what is a decreasing function. Okay, so if I have a function, right, okay, and the graph maybe somewhat looks like that. Okay, so this is what we call increasing function. And how do we define it? Okay, it is such that as x increases, okay, we find that y also increases. So this is what it means by increasing function. Okay, some examples of increasing functions that we have seen before, right, will be, for instance, a graph with the equation y equals to x. Okay, and after that also can consider y equals to e to the power of x. Okay, these are some examples of increasing functions, right? Now, what do you think decreasing function will mean? If we understand that increasing function will have to look like that. Decreasing functions will have to mean that we have a graph that maybe looks something like that, okay, whereby as x increases, we see that y actually decreases. Okay, so this is just a sketch, just for us to get an idea. Okay, I don't know whether there's an equation to match this curve or not. Okay, but some examples that we have seen before would be maybe y equals to negative x plus 4. Okay, so this will be a decreasing function itself. Okay, or y equals to negative e to the power of x. That will also be a decreasing function. Okay, do we all have the idea first? Alright, but there are certain functions that are not always increasing and not always decreasing. What do I mean by that? Okay, it means that as x progressively from negative all the way to positive, as x increases, okay, we don't observe that the y is always increasing, or we don't always observe that the x is always decreasing. One such typical function would be, for example, our y equals to x squared function, our quadratic curve in this case. Okay, whereby it is only for a particular segment, a specific segment, that we see that this part over here, when x is more than 0, okay, we find that y is actually increasing. So this part over here is what we see as increasing function. Okay, whereas on the other side, okay, of the x-axis, when x is actually less than 0, we find that the y is decreasing. So it is always from small to big. Okay, so when x is increasing, okay, we find that our y is actually decreasing. So it is only a decreasing function for a specific interval, and that is when x is less than 0. Okay, so it might not have to be specific, rather it might not have to be all values of x, okay, such that this function will always be increasing. Okay, it can be just a very specific kind of interval, okay, where we describe that it is an increasing function, or describe that it is a decreasing function. Okay, so what we observe over here, so after understanding what is an increasing and decreasing function, how does this then relate to our derivative? Okay, we understand our derivative describes the gradient of the tangents, right? Okay, so if you look at the tangents that we are going to draw, okay, on our this part over here, the increasing part, okay, what do we observe about the gradients? Are they actually positive or negative? The gradients of these tangents will be positive, right? Okay, so this will tell us that dy over dx, which describes the gradient, it will be positive, okay, it will be positive if y equals to fx is increasing. Okay, and then after that, if you notice how the gradients, or rather how the tangents are like, okay, in the decreasing set function part, okay, the gradients will always be negative. Okay, you can try to look at the gradients or the tangents, the gradients of the tangents that we draw, okay, for these functions. This will always hold true. So dy over dx less than 0 if y equals fx is decreasing. Let me face it. Okay, so dy over dx, if we see that the gradient itself is actually positive, the derivative is positive, then we can conclude that y equals fx is increasing, and if the gradient itself is less than 0, then y equals fx is actually decreasing. Okay, so we will make use of the derivative to determine for us whether the function is it increasing or decreasing or not. Okay, so this is the focus that we're going to have today. Any questions up? Let's look at try 5. Okay, given that we have this function 1 over x minus 1, we want to show y is decreasing for all x. So that means that for all values of x, we're very sure that our derivative will always have to be less than 0 because we're looking to prove that it is decreasing. Okay, so in order to prove that it's decreasing, the evidence that we need to show will be that the derivative is less than 0. So with this function, we will differentiate it . And the derivative is going to be negative 1 over x minus 2 squared. Okay, you cannot just stop here. You need to be very clear in your explanation. Okay, so you need to say that since x minus 2 squared, okay, is always positive, or rather you can put a symbol, it's more than 0, right, for all values of x. Or you can follow the statement for all x. Okay, so since this part over here is going to be always more than 0, and then there is a negative sign on the outside, okay, the entire expression will actually be negative. So therefore, dy over dx will have to be less than 0.
Oh.
Yes. Sorry? I can't hear. Oh, x. Why? Oh, okay. Oh, it's fine. Sorry.
So,
Yep.
they ask to show that y is decreasing for all x. That means this y expression is A decreasing function.
Yes. So how do we show that it is a decreasing function? We have to actually prove by the derivative. You understand? You understand what I'm saying?
How?
Huh? Anybody doesn't understand this question? Okay, shall we move on? Okay, let's look at try 6. Okay, we're given this function and we want to find the range of values of x for which y is actually increasing. So we want to find the exact interval, okay, whereby this is going to be increasing. Because actually if you are familiar with this is a cubic function. Our cubic functions graphs, right, okay, somewhat looks like this. Okay, a sketch, a general sketch will actually look something like that. Okay, so looking at this graph, surely it is not always increasing. It is only a particular interval whereby it is increasing, and then for a particular interval it is decreasing. Okay, so now we want to find out what is that particular interval that will allow for the function to be increasing. Okay, so since you're looking at when y is increasing, our derivative that we're supposed to be looking at should actually be dy over dx is more than 0. So we first find out what is the derivative. So finding that our dy over dx is equals to 6x squared plus 6x minus 12. Okay, if I were to factorize this, we will be getting this. The reason why I'm factorizing it is because, okay, we are looking at dy over dx more than 0. So that means that our 6 times x plus 2 times x minus 1 will be more than 0. Okay, so this goes back to our very first chapter in A Maths whereby we learned about quadratic inequalities. Remember that? Okay, because this is a quadratic expression, factorize it, okay, then more than 0. Okay? So then after that, we will be looking at this part because I can divide the 6 away. How do we actually do quadratic inequalities? Do you remember? We need to draw the graph thing, right? Okay, then after that, down here negative 2, down here 1. More than 0, that means it's at the sides. So therefore, x is less than negative 2 or x is more than 1. Okay, so in conclusion, y is increasing for x less than negative 2 or x more than 1. Does anyone not understand what I'm trying to do? Okay, so this actually somewhat follows the idea that we have from our sketch because it is only for a particular interval, okay, that we see over here, that it is actually increasing. So it is only increasing on this part here and this part here. Okay, so if it makes sense of this interval with the graph that I sketched out. Okay, it is when x is less than negative 2. When x is less than negative 2, we find that every part of it is actually increasing. Okay, and then after when x is more than 1, So every part more than 1, you find that it is increasing as well. Okay? So our understanding of all our maths concepts are consistent with one another.
What is the derivative?
Is what? Cubic.
Cubic.
Cubic. Then usually it will not give you a cubic one. Yeah. Because we cannot solve a cubic inequality, you see. Yeah. We can't do that. So that means that it is very unlikely lah. Unless the cubic can be factorized in a certain way. Okay, I'll show you in this example. Okay, this is the last example for this section. Okay. Yes, it will only be more homework. Okay. Okay, so just now Bernard was asking what if it's cubic, right? Okay, so for cubic, it would not be too difficult such that there are 3 different factors, because if 3 different factors, we don't have the skill to actually find the intervals. Okay, but in this case, right, we find that if I were to differentiate it, okay, remember if I have fx